Hello everyone and welcome once again to my channel and please do subscribe to our channel if you like the videos because many people watch the videos but do not subscribe to the channel. Okay, so today we are going to start statistical physics, which is an important topic for your examination purpose. It is a part of paper number 1 and I am going to put it in the playlist. Okay, paper 1 playlist. So already nuclear and particle physics was going on. Then why I am starting statistical physics? The reason is that since many days I was not able to take the paper 1 classes. So let's first of all complete the paper number 1 also side by side so that everything is balanced. Okay, nothing is unbalanced. Now, probability, the definition of probability and principle of equal a priori probability. I am giving you a homework. Okay, homework is that homework is that uh, learn the definition of probability. Learn the definition of probability. This is homework number 1 and second homework is principle of equal or priori probability. Okay, learn the principle of equal or priori probability. Okay, so learn the definition of probability and learn the principle of equal or priori probability. This you have to do from the book. Okay, this is not a big fact. Okay, you can use Google also for this. For this you can use Google also. There is not a big deal in it. Okay, so let us start with our important topic of statistical physics, that is macrostate. Okay, so let us write macrostate. Okay, sorry, just a second. Macrostate. Now I will write something over here. You will have to just write along with me. Okay, write along with me side by side in your notebook. Consider. Okay, macrostate is the heading. Now write over here. Consider a system of n particles. Consider a system of n particles confined under the heading macrostate. Under the heading macrostate, you have to write this. Consider a system of n particles confined to a space of volume V. Here n is of the order of 10 to the power 23. Now, what is the meaning of this? The meaning of this is very simple, that you have to simply consider a system of n particles. Okay, there will be a system of n particles and this system of n particles will be confined to a space of volume V. So it is very clear that suppose if there is a gas, suppose there is a gas consisting of n particles, then that gas will be confined to a space of volume V, means the gas will be inside a container. Okay, so that container will have a volume V. So such a system is there. Now whenever we basically study the statistical physics, we are usually taking the number of particles to be very large. Okay, whenever we study statistical physics, we usually take the number of particles to be very large, very huge. Because for a very small number of particles, suppose if there are only 15 particles or 20 particles or only 100 particles are there, suppose, then in that case the bulk property cannot be determined. Okay, because it is not a bulk, because the material is not itself in bulk. Only 15, suppose there is a gas in a container and only 15 atoms of the gas are there in the container. So in such a situation, that is not an ideal situation. In such a situation, you can study the atoms on one-on-one basis. Okay, under such a situation, you can study the atoms on one-on-one basis, because only 15 atoms are there. So you can study the atoms one by one instead of going for the average properties or bulk properties. But but in order to apply the statistical physics, it is very necessary that your n should be of the order of 10 to the power 23. Your capital N, that is the number of particles which is confined to the volume V, that should be of the order of 10 to the power 23. Only then you can apply the bulk properties. Okay, only then you can apply the bulk properties. So this is a fact. Okay, now here n is of the order of 10 to the power 23. So we assume that n tends to infinity and v tends to infinity. Since we are going to study the classical statistical physics first, statistical physics is of two type. Okay, a lot of sound disturbance is there. Just a second. Okay, wait, sir, just a second. Lot of sound disturbance is there. Okay, so now it's okay. See, statistical physics is studied under two era. Okay, one is the quantum era and other is the classical era. And the classical statistical physics means your Maxwell Boltzmann. Maxwell Boltzmann is your classical statistical physics. So in this classical statistical physics, the number of particles is of the order of 10 to the power 23. So we simply assume that n tends to infinity and v also your tends to infinity. Volume also tends to infinity and n also tends to infinity. Okay. Now you will understand this thing, that why the volume has been taken as tending to infinity. It is the thermodynamic limit. Okay, thermodynamic limit means now if you remove the container of the gas, suppose if you put the gas out of the container, what will happen? It will expand, the gas will expand. Okay, so it will occupy infinity volume. Okay, so basically we assume that n tends to infinity and v tends to infinity for such a system. Okay, in classical limits, under classical limits, as compared to the volume occupied by the atoms of the gas, as compared to the volume occupied by the atoms of the gas, the volume overall occupied by the gas is very huge, so v is also infinity. Okay, let me show it over here. Suppose this is your container. Okay, suppose this is your container. Suppose this is your container. Okay, then what will happen in this container? Suppose this is your container, then simply some gas will be there inside this container. So the atoms will be there like this. Suppose this is an atom number 1, atom number 2, atom number 3. Okay, so the atoms will be very much tiny as compared to this container. Okay, atoms will be very much tiny as compared to this container. If we take the whole volume of this container, then the volume of this container will be very huge. Okay, v tends to infinity means volume of this container will be very huge as compared to the volume occupied by these individual atoms. Okay, of this gas, atoms of this gas. If we even add up the, suppose there are 10 to the power 23 such atoms, tiny atoms. Even if we add the whole volume of these 10 to the power 23 atoms of the gas, still, still the volume of the container will be very huge as compared to the volume occupied by the atoms of the gas. So that's why we are taking V tending to infinity. That is your thermodynamic limit. Okay. So this is your what? Thermodynamic limit. Thermodynamic limit. Such that such that such that the particle density particle density is your what? N is equal to capital N by V. What will be the particle density? Total number of particles divided by total volume. That is your, now your material density is your mass upon volume, right? Material density is mass upon volume. So if we take the material is measured by mass, so that's why material density is mass upon volume. But particle density will be measured by the number of particles. So number of particles divided by volume will be your particle density. Okay, so small n equal to your capital N by V remains fixed thermodynamics such that the particle density n equal to n by v, this remains fixed. Now ratio of two very huge quantities, n tends to infinity, v tends to infinity, means n is very huge and v is very huge. So ratio of two very huge quantities will be a what we can say, smaller number. Okay, it will be a limited number, it will not be infinity number. Okay, so small n equal to n by v remains fixed, remains fixed remains fixed at a particular value. This ratio remains fixed at a particular value. Okay. In this case, in this case, the extensive properties of the system, the extensive properties of the system, that is proportional to n or to v. This is 2, okay? To v, and the intensive properties. Okay. In this case, the extensive properties of the system, okay, become directly proportional of the system right over here, become directly proportional. Okay, become directly proportional, put over here in this place, become directly proportional. I forgot to write over there. Become directly proportional to the size of the system. To the size of the system, that is proportional to n or to v, and the intensity properties become independent. Okay. Now I will explain the meaning of this. Okay. So hopefully you have written this in the notebook. So n particle system is there which is confined in volume V. N is of the order of 10 to the power 23. So we assume that capital N is equal to infinity, means tending to infinity, and V tends to infinity. And yes, both of them are huge numbers, so their ratio will be a limiting number. So small n will be a limited number. So it remains fixed at a particular value. Okay, number of particles per unit volume will be fixed to a particular value, that is the particle density. Okay, so in this case, the extensive properties of the system. Now what do you mean by extensive properties and what do you mean by intensive properties? Extensive properties are those properties of the system which depend on the mass, and intensive properties are those properties of the system which do not depend on the mass. Okay, extensive properties are those properties of the system which depend on the size of the system, that is amount of matter in the system. Extensive properties are such properties of a system which depend on the amount of matter in a system. But intensive properties are such properties which do not depend on the amount of matter in a system. Okay. So you must you may learn this in the thermodynamics. I will teach you when I teach you classical thermodynamics. Okay, this is basically statistical thermodynamics. But when I teach you thermodynamics, normal thermodynamics, so at that time I will tell you what are extensive properties and intensive properties in detail. But for the time being, just consider like this, that suppose I talk about density, material density. Then density of a material is given as mass upon volume. So if I have, suppose 1 kg iron, suppose I have 1 kg iron with me, and suppose if I have 2 kg iron with me, so, do you think the 1 kg iron and 2 kg iron will have different densities? The answer is no. 1 kg iron will also have same density, and 2 kg iron will also have the same density. Only difference will be in their masses. Okay, so density, material density will be same because both are made up of iron. So density, material density, that is mass density, is your intensive property because it is independent of the amount of system. Even if you take 2 kg iron and even if you take 1 kg iron, it is independent of the amount of material. Okay, so as it is independent of the amount of material, so what? So it is clearly an intensive property. Your mass density is an independent of amount of material. So that's why your mass density will be an intensive property. But suppose if I talk about volume, then volume will be an extensive property. Why volume will be an extensive property? Because if I take 2 kg iron, that 2 kg iron is going to occupy more space as compared to 1 kg iron. Okay, that's why. So volume depends on the amount of material in the system. More is the material, more will be the occupied volume by the system. Okay, so that's what I was saying, that your small n, which is capital N by V, that is material particle density. Okay, particle density, that is, remains fixed at a particular value. Okay, because it is an intensive property. Okay, it is not an extensive property, because number of particles per unit volume will be an intensive property, not extensive. So in this case, extensive properties of the system become directly proportional to the size of the system. It is a common sense thing that extensive properties of a system become directly proportional to size of the system. Told you right now. Okay, that is proportional to number of particles, or number of, either you say that the extensive properties are directly proportional to number of particles of the system, or either you say that the extensive properties are directly proportional to the volume of the system. You say like that because extensive properties are dependent on the amount of matter, and amount of matter depends on the number of particles and total volume occupied. Okay, so your extensive properties will depend on capital N and capital V. Your extensive properties will be directly proportional to capital N or capital V, but your intensive properties will become independent of capital N and capital V. Okay, your intensive properties will become independent of capital N or capital V. So that's what has been written over here. Okay, that's what has been written over here. So just a second, let me take the next slide and I will write over there now. So total energy of the system. So total energy of the system, what does it become? Total energy of the system E is equal to summation I N I E I. Okay, this is equation number 1. Now, what does this mean? Total energy of the system means summation I N I E I. What does this mean? Suppose there are n1 particles with energy E1. Okay, n1 particles with energy E1 means there will be total of n1 particles each having energy E1. Okay, total n1 particles will be there each having energy E1. Then there will be total n2 particles each having energy E2. Then there will be each particle has energy E2. No, not it's not like n1 particles are overall having energy E1. No, not n1 particles are not having overall energy E1. Not n2 particles are having overall energy E2. No, each of the n1 particles, total n1 particles are there, and each of the n1 particle, each of the n1 particles has energy E1. So total energy will be n1 E1. Okay, by unitary method. Then n2. So total number of particles is n2, and each of the n2 particles, each one has energy E2. So total energy will be n2 E2. Okay. So similarly, if you keep on adding, what is it equal to? It is equal to n1 E1 plus n2 E2 plus n3 E3. Okay, so on and so forth. Okay, up to whatever may be the number at the end. Okay, so total energy of the system is like this, where Ni is equal to number of particles each with energy Ei. So right over here, Ni is equal to your number of particles each with energy Ei. Number of particles each with energy Ei. Ni particles will be there each with energy Ei. Like over here, n1 particles were there each with energy E1, n2 particles were there each with energy E2, n3 particles were there each with energy E3. Okay, so like that. So Ni particles are there each with energy Ei. Now total number of particles, it is a common sense. Okay, total number of particles, your total number of particles what is it equal to? Your total number of particles is equal to capital N, which is equal to your summation I Ni. This is a common sense thing. Total number of particles will be equal to N1 plus N2 plus N3 plus N4, because E1 energy level has N1 particles in it. E2 energy level has N2 particles in it. E3 energy level has N3 particles in it. E4 energy level has N4 particles in it. E ith energy level, which is the highest energy level, E ith energy level has Ni number of particles in it. So total number of particles will be simply equal to N1 plus N2 plus N3 plus N4 up to Ni. Okay, so total number of particles is like that. So now this is your equation number 2. Okay, for such a bounded system, okay, for such a bounded system, the now write over here, for such a bounded system, the energies of particles EI must be discrete. Now, for such a bounded system, the common sense is that the energies of particle EI must be discrete, right? Because if they are continuous, then summation cannot come. Suppose this, for example, E is equal to your summation I Ni Ei has been there. Okay, summation I Ni Ei. So over here in this particular case, suppose if the energy levels were continuous, then summation symbol cannot be used. Over here the energy levels were discrete, because E1 energy level was there, then directly after E1 E2 was there, then after E2 directly E3 was there. So the energy levels were discrete like this. This is your E1, this is your E2, this is your E3. So your energy levels were discrete. This is your E4. Okay, so these are discrete energy levels, right? So these are basically your quantized type of energy levels. Okay, these are discrete energy levels. So N1 particles will be over here, N2 particles will be over here, N3 particles will be over here. Okay, N4 particles will be over here, right? So, so right over here, for such a bounded system, the energies of particles EI must be discrete. Okay, and in quantum mechanics, the energy levels are discrete, right? In quantum mechanics, the energy levels are discrete. So, like the particles in 3D box, you will learn this in the quantum mechanics, which I haven't taught you yet. I haven't taught you yet the quantum mechanics. So, like the particles, so for the time being, just mug it up. Eventually, you will clearly understand this thing. Like the particles in 3D box, Schrodinger wave equation, 3D box, okay, 3D box model you will learn in quantum mechanics. So like the particles in 3D box, your energy will be given like this, right? How your energy will be given? Pi h bar square, okay, pi square h bar square, nx square plus ny square plus nz square, okay, divided by 2ma square is equal to pi h bar square, okay, nx square plus ny square plus nz square, okay, and divided by it will be your 2m, okay, a to the power 3, it will be 2 by 3, okay. So this 3 and 3 will cancel out and it will give you 2 once again. Okay, these 3 and these 3 will cancel out and it will give you 2 again. So like that I have written it. So your energy is now your A cube. What is your A cube? A cube will be your volume of the cube. Okay, A cube will be your volume of the cube. So what is your energy? How is your energy now? So your energy is clearly inversely proportional to a to the power 3 2 by 3. Okay, so we can eventually write this a cube is equal to your volume of the cube basically. So your energy will be inversely proportional to 1 upon v to the power 2 by 3, right? So I can write over here, so just write over here that it will be equal to all these things are constant, right? Pi square h cut square, over here it is pi square. Okay, so pi square h cut square, all these things are constant. Okay, so I can write over here that inversely proportional to v to the power 2 by 3. Okay, so you, like that you can write. So the specification of actual values of parameters. Now, as your E has come out to be inversely proportional to V to the power 2 by 3. So from here you can clearly understand that the specification of the actual values of parameters NVE, right? The specification of the actual values of parameters N, comma V and E defines the macro state of the system. Okay, defines the macro state of the system. So your macro state is basically what? Macro state. I am saying about macro state. Okay, macro. So macro means bulk. Okay, macro means bulk. So and capital N is your total number of particles. V is the total volume occupied by the particles. E is your total energy of the system. So all these are what? Basically macro properties. Macro property means bulk properties. Okay, bulk properties. These are not quantum properties. These are bulk properties or macro properties, means large scale quantities, large scale properties. So this is how macro state can be defined. Now we will learn about micro state, but before that I will take a break.